Hey students, let us explain this exercise. Uh, in this case, we have a 55 kilograms astronaut who weighs 180 newtons on a distant planet, and he's pondering whether she can leap over a 3.5 meters wide uh, chasm without falling in. If she leaps at a 15-degree angle, what should be the initial speed that she need to clear the chasm? So basically, what they give us here, they give us here a chasm. We know there is 3.5 meters wide, and we have this astronaut over here that is going to try to jump to pass over the chasm. So it's going to be landing on the other side, right? So the question here is what the initial speed needs to be so she can clear the chasm, you know? Well, the first we need to find out here is what is the acceleration of gravity in this planet. So we know that the mass of the astronaut is just 55 kilograms. We know that the weight is 180 newtons. We know that weight is equal to mass times gravity. So if we solve for gravity, which is weight over mass, it would be 180 newtons divided by 55 kilograms. So we get that the gravity, acceleration of gravity in this planet would be 3.27 meters per second square. This acceleration of gravity is lower than the acceleration of gravity on the Earth, right? So we are in a planet where the acceleration of gravity is lower than the acceleration of gravity on the surface of the Earth. Now, what we need to understand about the motion of the astronaut when just jump, right, to cross the chasm. Well, uh, it's going to move as a projectile. So as is jumping to pass over the chasm, you we have, right, that in the x direction it would be in uniform motion, right? So here is uniform motion. So it's motion with no acceleration, and the equation that describes this, the displacement in the horizontal direction, that is basically, what are we working with? It's gonna be b sub 0 x times the time. Now, of course, right, there would be also a component of velocity here, right, in the y direction. Okay, there is another component of the velocity here in the y direction. The angle would be 15 degree. So we know this angle here is 15 degree. So this is b sub 0. So we know now that b sub 0 x would be b sub 0 cosine of the angle, that in this case is cosine of 15 degree, right? So now we know that x would be b sub 0 cosine of 15 degree times the time. So we know what is x. X would be the width of the chasm. We don't know what the initial speed must be, and we don't know the time of flight. Now, we know that working in the vertical direction, so working with the other component of the motion, we can find this time of flight using equation of kinematics. The only thing that we have to remember is that in this direction, in the vertical direction, we have motion with uniform acceleration. Motion with uniform acceleration. And then we can use this equation to say that the final velocity in the y direction is equal to the initial velocity uh, in the y direction plus acceleration time. We know that the acceleration in this case would be minus gravity, right? Because the gravity is pulling, right, the body toward the center of the planet. So it's pointing downward, so it's going to be negative. So we know that b final y is equal to b initial y minus gt. Now, if we calculate the time, if now we try to calculate the time, right, for the highest point of the trajectory, we know that the highest point of the trajectory, which is this point over here, right, the velocity final at that point in y would be 0, right? So we're gonna find the time, needed to go from this point where the astronaut is jumping to the highest point of the trajectory. The time of flight would be equal to 2 times that time, right? So I will be taking this final velocity in y0, so I can say that the initial velocity in y is equals to gt. So initial velocity in y would be initial velocity times the sine of the angle, 15 degree. We can solve for, in this case, t, so we get that t, the time needed to reach the highest point of the trajectory will be b sub 0 sine of 15 degree divided by g, right? So of course now we know that the time of flight will be 2 times that time, so the time of flight will be 2 b sub 0 sine of 15 degree over g. This time of flight, right, is the time that we need to plug it in where here, right? So we have that this time is common for the horizontal motion and for the vertical motion, for the horizontal component of the motion and for the vertical component of the motion. So I will replace this t by the time of flight. So we can say now that x is equal to b sub 0 cosine of 15 degree times t, which is 2 b sub 0 sine of 15 degree over g. So we multiply and we get that x is equal to 2 times b sub 0 times b sub 0 is b sub 0 square. Then we have a sine of 15 degree cosine of 15 degree over g. Now we know from trigonometry that 2 times sine of 15 degree cosine of 15 degree will be sine of 2 times 15 degree, will be the sine of the double angle. So x would be b sub 0 square sine of 2 times 15 degree over g, right? So of course this would be 30 degree, right? So we know this x, we know that x is the width of the chasm, so it's 3.5 meters. right? We know the gravity because we calculated, right? We know that it's 3.27 meters per second square. So we are ready to solve for b sub 0. So if we solve for b sub 0 here, we're gonna have that xg, right, is equal to b sub 0 square sine of 30 degree. So we will divide by sine of 30. So we get that xg divided by sine of 30 degree is equal to b sub 0 square. So b sub 0 would be the square root of xg divided by the sine of 30 degree. So now we can find b sub 0 easily because we know x, which is 3.5 meters, times the gravity, which is 3.27 meters per second square, divided by the sine of 30 degree, and we find that the initial speed needed to leap over the chasm would be 4.8 meters per second. So with this speed, initial speed, the astronaut is going to leap over the 3.5 meters wide chasm, right? So super important here to combine, the motion that we have in the horizontal dimension, in the horizontal direction, with the motion that we have in the vertical direction, because this is basically like a projectile problem, but we have motion in two dimensions. So I hope the solution of the exercise was interesting for you, and I ask you that you please subscribe to my channel so you can support my work. Thank you.